I will talk about an industry view about the high temperature challenges for bulk thin film measurements. So we, Exact Systems, are a manufacturer of test equipment for piezoelectric materials, and we joined this project to improve the traceability and also the high temperature capabilities for our systems. I will give a short overview. So first I will introduce the double beam laser interferometer technology for thin film measurements and the low strain measurements. And this is also industrially used and what the special requirements are there. And show some of the reference and repeatability measurements, which are, I think, one of the most important points for industrial use. Then the work for extending the temperature range from previous room temperature, and then go over to bulk sample measurements using single beam laser interferometer and the piezoelectric evaluation system. The developments we did there also to go to high temperatures, and the same there, high temperature measurements and also repeatability and some reference measurements. So to give an overview, we have three main fields. So one is a PES system for bulk piezoelectric characterization. Then we have a piezoelectric transducer test bench called system, which is also used for multi-layer actuators where you can apply forces. And third is thin film measurements. One is for in-plane coefficients and the D33 effective coefficients, which I will introduce now. So I think we've seen this before. Just to summarize, we measure the indirect piezoelectric coefficient by applying a voltage and measure the strain. So this is, well, somehow straightforward for bulk materials. So we just measure the strain by a laser interferometer. And if we go over to thin films, we have additional issues. So the difference here is that we have a substrate where the piezoelectric material is put on. So the substrate will clamp actually our piezoelectric material, and this will give us a different coefficient because it blocks the lateral motion. So the effective D33 or the effective strain that we measure on the film is reduced by this clamping. And
can we get off this one? Okay.
So we will receive an effective coefficient which is reduced by the D31 and the compliance of the film, which was introduced already in '94 by Lifkin Goldmans. There, and additionally to this effective coefficient, the substrate creates a motion of our whole sample, and this will give us a typical bending motion of the whole substrate, and this is easily orders of magnitude higher than the actual elongation of the film itself. And that is where the double beam laser interferometric method was developed to be able to measure the precise strain of the film itself, which is a few nanometers or even picometers in range. And there's also further influences of the substrate, which I will not focus on here, but that, for example, creates a pad size effect because the substrate is compressed and so on. These are further challenges that are part of other work as well. So the principle here, we already have seen two types of interferometers. This is a multi-cylinder interferometer, so we have a measurement beam that comes from a stabilized laser source, goes on the top of the sample, then is directed to the bottom of the sample and interfered with the reference beam, and then we get the difference between the top and bottom motion, so the elongation of the sample in between the two beams. So basically we have a point measurement, but it measures the point on top and bottom, so we exclude the sample bending. And so this, in terms of industry use, this is used for, or desire to be able to measure on wafer level. So we need a very high repeatability. It's probably more important than the absolute precision, because you want to monitor what your wafer to wafer change, for example, is, or your distribution across a wafer if you produce a thin film. And what we typically use is a quartz crystal for verifying the measurement. And this has been used already in the beginning to monitor the performance and the resolution of the interferometer. So we have around 2.2 picometers per volt. And this is how we can check the resolution of the system. So we can go down below picometers in the system resolution. Maybe what I could show also, this is the repeatability. So usually we take a couple of quartz measurements to monitor the stability of the system. And this is data we took from an industrial system over, for example, 16 months, and we still way below 0.5% repeatability in the measurement. But still the absolute value is of interest, and that's why we want to have a consortium where we can develop a standard. Because even for quartz, it's not 100% sure value and what it depends upon. So this is a typical wafer distribution. So this is a D33F of a piezoelectric PZT film, and the desire is to have a very high repeatability and precision across the whole surface. Now, the challenge is to do this under temperature because we have a quite long beam, and as you heard already, that the refractive index of air changes, has a lot of influence, and that's why we have made very small volume, and this allows us for manual measurements on small pieces that can be heated, and to do this under temperature as well. And just a rough calculation, in 2 centimeters of hot air, a 1 degree change already generates 8 nanometers of deflection, which you would virtually see. So that means you would have to maintain a stable temperature. And what I could mention, this interferometer is a working point stabilized interferometer. So as you saw the sine waves before, we picked the center, and the beams, the interference pattern is kept stable, and then we just monitor the deflection out of this working point, which is kind of linearizing our phase, and but it limits also the maximum deflection that you can measure to a fraction of the wavelength. But for a typical PZT film, it's like 5 nanometers in this order of magnitude. So we have developed within the project to go up to 600 degrees C in this stage, and also being able to cool down in this environment. So for a reference, on one hand we took the quartz, which I'll show later, and we take aluminum nitride films because this is a stable material. It does not show a ferroelectric behavior, but a piezoelectric behavior, which is rather low, around 5 picometers per volt. But it's stable, and we showed also that it's, in this case, stable up to 450, and seems to be almost reversible. But you can see that the deviation is much higher across the temperature, mainly due to fluctuations. So we have around 4% of standard deviation if we take the whole run. But this means 0.2 picometers per volt of standard deviation, which allows us now to monitor thin film behavior to high temperatures, and this is something really new and useful also for PCT characterization. So some effort was taken into the temperature calibration, as we also have seen before, and we took already a commercial stage, and we're also surprised that there's a huge difference between your actual heater stage temperature and the sample. So we took Mercur and steel as two materials which have about a factor of 10 different thermal conductivity, but still they are within, let's say, 5 degrees. And if we fit this to get the sample temperature, we can get a deviation of around 1.5 Kelvin plus minus across heating and cooling cycles up to 600 degrees C. So this is the first results we did on PCT. thin films, and what you can nicely see is, so the dashed line here is the normal electrical hysteresis at room temperature, and the dashed line here, this is the butterfly loop. And at high temperatures, our electrical values are mainly influenced by leakage currents, and that means we can't really trace the polarization. Of course, this is also frequency dependent, but we can still see that the deflection or the piezoelectric activity is still quite high. It's still about 3/4 of the room temperature value, and this is measured at 400 degrees C. So this seems to be quite a good material in this case, and this is the small signal, so this is using just a triangular excitation, similar as you showed, averaging, like say, like 100 loops. And this is the small signal, so where we apply an AC signal and we change the DC bias, so you can see what the D33 versus the applied bias does. So at 0 volts, there's almost no D33, but if you increase the voltage, then you still have a rather high value here. And the capacitance is drawn in red here, so there's similar behavior.
And this was PZT?
Yeah, this was PZT.
And 400 degrees, and you still have?
Yes.
How come?
Good question. It's not our material, but I don't know exactly the composition.
But maybe it's just the difference in temperature measurement. This is 50 degrees that you have between your measured sample. No? Okay. It's calibrated, right?
Yes.
Some of the
mysterious PZT then.
60-40 would give you 400 degrees.
Yeah.
Okay.
But it's also on a substrate, so
So it's not PZT then.
some of the work that we've done on bulk on some soft PZT, and I would imagine the same thing would happen on hard PZT, is that you still see piezoelectric activity significantly above the Curie temperature for high fields, and because this is biased, it essentially becomes electrorestricted.
yeah.
Okay.
Yeah, you can see if you would have a 0 volt, then there would almost be no D33 left, only if you excite it at a high field. And this is something we see with the bulk as well. Right. So this is a different material. We can see the small signal excitation without poling it during the application, that it's already disappeared at 400 degrees C, and it's getting electrorestrictive after that only. And if we apply a large signal, so excite the material all the time, we still maintain it broke down at 350 degrees C, but that the value is more constant than here, where it drops down. And this is a bulk sample which we also measured in the DBLI system at a low field, like 10 volts and 1 kilohertz, and we could see that up to 550 degrees C, at the turning point here, the black dots mean that it's running into compliance because we only have 1 kilohertz, but it's much different from the resonance at high frequency. For an actuator, for example, you would have lower excitation frequencies and also different behavior. Okay, and from the bulk, I will step over from the DBLI to the piezoelectric evaluation system using the single beam interferometer. So this is the setup we use here. So it's the basic parts is a ferroelectric analyzer, commercial single beam laser interferometer, high voltage amplifier, an impedance analyzer can be attached, temperature controller, and the various types of sample holders which can be selected according to the samples that are needed. And of course it offers all the electrical measurements and at the same time the measurements of piezoelectric properties. So for different sample types we have different sample holders. So the typical bulk ceramics, we have a sample holder which establishes a point contact, and for multi-layers we have sample holders which allow to apply a force. So So the sample holder has to be adapted to your sample shape, basically. And the laser interferometer can be attached to the various sample holders for the evaluation. So this is the sample holder for bulk materials. So they have a very small heating volume, and the sample can be easily placed inside and establish the point contact to the sample from the top and the bottom. And we measure on the top by a single beam laser interferometer on the top surface by a rod, basically, which has no big force, so that we are independent on the electrode materials. So, for example, silver pasted or a degradation of the electrodes or planarity does not have a big effect here. It's mainly a matter of precise sample placement, and can also maintain a fast heating and cooling rate to speed up the test in this setup. So within this project we developed the higher temperature capabilities. So we had a version from -100 degrees C to 600 degrees C, and the main limitations are actually the materials that you can use. So for going to high temperatures, you must have a material which still establish a good contact over the whole temperature range without degradation. And if you put in the sample and pick it out, you must not deteriorate your setup. So, but being able to measure many samples without destroying the electrode materials. And at 800 degrees C, you can see that it's already nicely glowing in this case. So uncertainty evaluation was also a part of the project, and in this case it sounds rather simple because we just measure the displacement and voltage, of course additionally the charge, but there's still a lot of influences that have to be taken into account, like especially vibration influences and change in your airflow or thermal drifts, and all of this was evaluated for a certain range of measurement parameters, so that the goal to be more precise than, or in the range of 1%, could be achieved, but the reproducibility is still around 2%, and this is still focusing to do more precise handling of the samples. But still it should be easy to maintain and operate. So this is a typical small signal measurement, as I showed before. So we apply DC steps with a superimposed AC field, but at a usually much lower frequency as in the resonance case. And then you can see the DC bias dependency of your D33. And in the resonance measurement, you would only see the 0 volt point unless you have a special circuitry to be able to apply that DC bias. And for the large signal, the typical is the triangular excitation. And this is, for example, the difference between a room temperature and this is PZT as well at 280 degrees C. So you get, the loop gets very narrow, and you can automate this over temperature, so you can monitor the change of various parameters over temperature and define your test pattern accordingly. And this was now also extended for the high temperature values. So this is for the piezoelectric sample holder. We did also temperature calibration using a similar setup, and we could also see that there is a similar change in temperature as in the DBLI system, and also the method gave us some ideas to improve that from around ±5 Kelvin to ±2.6 Kelvin now. If you raise the temperature and go back to 0, and the heating rate here was about 10 degrees C per minute, so that you can run a sample sweep within 1 day. And we did some comparison measurements. I think Paul will show more details on that, but that was just the quartz, and we could see On the DBLI we have much lower amplitudes, but we could see a similar behavior across temperature. And on the PS system we apply 2 kilovolts, which gives us about 4 nanometers, which is really close to the resolution limit of the laser, and we already have to correct for crosstalk and so on influences, but at least the shape nicely fits. And the further work is to correlate this also with the impedance measurements on the NPL system. And this is a measurement taken on the bulk material, on the high temperature materials. And what you can nicely see here, this is actually an extreme case on this composition, that large signal measurements are now here in blue and yellow at 2 different frequencies. It's 1 kilovolt, and yellow is 10 hertz, blue is 200 hertz. And we can see at the high temperature that the large signal, which comes from a triangular excitation, is actually much bigger than your small signal, which is shown here in green, which is still 100 volts, so it's not really small, but we can see much different behavior. I think Paul, you will explain the process to explain the behavior, but this also shows that it's very different whether you do resonance analysis or apply large signal, for example, if you want to use the materials for actuation at high temperatures. So that means both kinds of characterizations are needed. And maybe to mention that at the high temperature here, it runs into current compliance, so the drop could be even less pronounced if we drive more power into the sample. And this is the individual displacement graphs. So you can see at lower temperatures the displacement starts to grow with temperature, and at high temperatures you can see the shape is changing, so you have something going on the material. And for even higher temperatures, for example the green loop, it's going down again, but this is also limited because the current is not high enough. And at the same time we monitor the current so we can get the resistivity. So in the range of 5 to 10 kilo ohms of the sample we are not able to. It's limited to 20 milliamps, depends on the amplifier of course. So you can see that the voltage goes down because the sample is really highly resistive, but you still can measure the displacement. But of course it's a different condition in that case. And this was a similar measurement on a different material, and you can also see the behavior here. Large signal behavior of 2 different applied voltages, or bipolar and unipolar case, which show a drop earlier. And the resistivity is plotted here, going from mega ohm range to a few kilo ohms. This is also a challenge. So you need a really big amplifier if you would like to drive the samples up, or very tiny pieces. This is the alternative. And this is just one slide, the resonance measurements. So we did also some resonance measurements in the same sample holder, so that you can compare resonance and large signal measurements within one setup. And it nicely agrees with the free mounted sample and in the sample holder. But so far it's only for the in-plane modes. Because of the contacting, it will have an influence on your D33 in that case. So it's used for D31 and KP measurements. So yeah, this is the lab we use, and the last workshop here shows a picture of the round, and this was done at Hexagon Aachen. So we also do some custom characterization, for example, and it's also very good to have this consortium to develop the traceability of these systems. Thank you very much.